Okay, so now let's use the knowledge we have to solve one particular problem. And you can see that the problem, and the reason that we solve this problem is to apply our methods. The problem is the EOQ problem. We know that we have solved the EOQ problem blah 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 like this, where H is the unit holding cost per year, K is the ordering cost per year, the ordering cost per order, okay, per order, and the capital D is the annual demand. The EOQ is just Q star, which is square root of 2KD over H. So this is something you know. What if we are procuring two products? In this case, we will solve this particular problem. Okay, we want to decide Q1 and Q2 as the order quantity of product 1 and product 2 so that we can minimize the total cost. In this case, the problem is separable, okay, because Q1 and Q2 are somewhat independent. So the optimal quantities will be the two EOQs, and you will be able to solve this problem with no difficulty, right? Because the problem is just separable. But in some situations, there is a constraint. For example, we may have only a limited space for these two products. You may imagine that we have a warehouse and the space is limited. For product 1 and product 2, they have their volumes. Okay, so the total volume of our inventory cannot be greater than our total space or warehouse capacity. If we have this constraint, then mathematically this problem becomes non-separable. We cannot divide this problem into two independent single-variate problems because the optimal quantity of Q1 may depend on Q2. The optimal quantity of Q2 may depend on Q1. Regarding the problem, if we are really talking about an inventory problem, actually we made some assumptions. First, we assume that the products can be in any shape. So we care about the sum of volumes. But of course, we know in practice, if these products cannot have a fixed shape, then even though their volume is not higher than the total space, it's still possible that we cannot store all of them, right? Well, practically, we have this shape issue. Let's assume it's not a big deal. Also, the constraint can also be modeling budgets or something else. So think about this. The constraint may be that we have a fixed budget for procuring products, okay? And we are requiring us not to procure too much, okay? Not to procure too much. Then this becomes a budgeting constraint. So that means conceptually this can be anything, requiring us not to order too much. Finally, by doing so, when we treat them as a warehouse and the volumes, we do not try to synchronize the procurement process. Okay, this the left hand side is the worst case, the maximum amount that we may use for ordering these two products. If we somehow synchronize the procurement process so that the two orders may not come at the same time, then we actually will not use this amount. But anyway, this is the worst case that we may experience, so setting this as a constraint is reasonable. Anyway, technically, let's solve this problem by assuming these are all satisfied. At least we can get some approximation. So now, the first thing we want to do is to solve this problem. We want to make decisions. We need to solve this problem, get numbers, and then make decisions. Also, we want to get some knowledge or get some insights from this problem. How does Q1 and Q2 affect each other? Which one will be larger in the optimal solution? When do we know the constraint is binding or not? We want to get some knowledge about it. To simplify the derivation and give you an easier time, let's say V1 and V2 are the same, and the h1 and h2 are the same. Now this is just some simplifying assumptions. You will see that for our derivation, these simplifying assumptions does not really matter. We still can apply the same method to solve problems without these assumptions, but with them, derivation can become easier. How to find a local mean? A local mean must satisfy the KKT condition, and in particular, it must satisfy the first order condition for the Lagrangian. Okay? You will see that this is the most important weapon that we will use for solving constrained nonlinear programs. Any local mean must satisfy KKT, and the first order of the Lagrangian is one of the KKT conditions. Okay, so let's first get the Lagrangian. This is the objective function. This is the Lagrange multiplier. Because we only have one constraint, so there's only one Lagrange multiplier. And then we have a constraint. Technically, you may ask, why there is only one constraint? Actually, we have three. Q1 non-negative, Q2 non-negative, and the capacity constraint. The thing is, first, technically we may choose to relax just a subset of constraints. Okay, in this case, I relax only one constraint and leave the other two constraints still there. Okay, then as long as my optimal solution satisfies the two constraints, I'm done. The problem has been solved. So that's one thing. For this problem, because we know quantities, order quantities can never be zero if we want to solve this problem. So there's no reason to be worried about the two constraints. That's why we choose to relax only this constraint. Okay? Or you can say that through some analysis, we can prove that Q1, Q2 non-negativity must be satisfied. They are redundant constraints. Why? If you plug in Q1 as 0, this is infinity, definitely not good. If we want to minimize the total cost, Q1, Q2 must be positive. Okay, and then that's it. So there's only one constraint to be relaxed. The first order condition for the Lagrangian is to take the Lagrangian and differentiate it with respect to Q1 and Q2. And then we will get something like this and something like this. Oh, sorry. This should be 2. Okay? Q1 square. And here is Q2 square. After this, we know these two equalities must be satisfied. The first order condition for the Lagrangian must be satisfied for any optimal solution. Okay, for any optimal solution. So, in any case, if Q1 and Q2 is an optimal solution, then we need to have this equality. How? For this particular thing, we can say that K1 D1 over Q1 squared equals lambda minus 2h. And for here is the same thing, right? This term must equal to h over 2 minus lambda. Okay? So these two things must be equal if we want to satisfy these two equalities. So this is very good. This tells us that Q1 and Q2, for them to be optimal, they must have a linear relationship. Okay, and the slope or the ratio is determined by K1 D1 and K2 D2. Of course, if we assume H are different, then H will enter somewhere here, and the format may become more complicated. But in this setting, Q1 and Q2 are linear. Okay, so this is some insight we get. Another thing we may say is that, okay, if we want to order more for product 1, we must also order more for product 2 if we want our solution to be optimal. That's some other thing we may say. Anyway, this is a very useful equality. So now, if we want to solve our two-product EOQ problem like this, for the unconstrained problem, if we ignore it, then this guy is the unconstrained optimal solution, right? This solution, we may verify whether it is feasible. If it is, of course, it is optimal. Okay, we know how to solve and get this. We know how to verify this. This may be done. And then if unfortunately the unconstrained optimal solution is not optimal, then of course we know the optimal solution must have the capacity constraint binding. And then binding constraint give we this equality, and then here we get another equality according to the first order condition of the Lagrangian. So we may solve these two equalities because any optimal solution satisfies these two equalities, and through some algebra we can get this. Okay, we can get this. So if the unconstrained optimal solution is feasible, it is optimal. Otherwise, we use our knowledge from Lagrangian to get the optimal solution. Okay, if you think about the KKT condition, or for example, the complementary slackness part, we know that lambda times W minus Q1 minus Q2 must be 0, right? Must be 0. And then in this case, what may we say? If lambda is positive, then this capacity constraint must be binding. Okay, this is the second case. Or if the constraint is non-binding, then lambda must be 0. Okay, lambda must be 0. And optimality requires the first order condition, the unconstrained first order condition, to be satisfied. Okay, so if we want to express the optimal solution in one sentence, then it's here. Okay, Q1 star and Q2 star depends on all the parameters. If this inequality holds, then these two numbers are the optimal solution. Otherwise, we have another optimal solution. So graphically, we may illustrate this idea. Let's see here. This is our feasible region, right? For different h, we may have different values for the unconstrained optimal solution. Let's assume we are using these parameters. And for example, when h is 1, we get this point. This is Q1, and Q1 is here, and Q2 is here. For h is 1.5, Q1 is here, Q2 is here. For several values of holding cost, the unconstrained optimal solution is infeasible. In that case, we will adjust the solution to Q head here, Q bar. Okay, this solution. Whenever the solution, the unconstrained solution, is infeasible, they are adjusted to this the boundary point. Okay, you can still verify that. For example, if the solution is h equals 1, geometrically the closest feasible point. Okay, is here, but it is not optimal. If we want to get the optimal solution, we move to the feasible region along this equality, and this direction is found with the Lagrangian, right? And this is the equality we found for Lagrangian. So it's not very surprising that all those points, or all those unconstrained points, satisfy this equality. If for the holding cost to be large enough, then in that case, the unconstrained optimal order quantities are small enough, and if it satisfies the capacity constraint, then it is optimal. So the optimal solution are all the possible optimal solutions for different h, for example, will fill up this particular line segment. According to the KKT condition or the first order condition of the Lagrangian, we know for primal feasibility, the optimal solution must be within this triangle. And then according to dual feasibility or the first order condition of Lagrangian, it must be on this equality. Okay, so that's why this is the set for optimal solutions. Okay, it must be one point on it. Or here, we may draw curves for the optimal order quantities. If the holding cost is small enough, then having inventory is not a big deal, right? So ideally, we want to order a lot. But if this is greater than the holding and the capacity 140, we will adjust the solution to 140. I mean, to adjust the sum to be 140. After it, the ordering quantity is not so large, and then we will order the unconstrained optimal solution. Okay, so this is how we solve this constrained two-product EOQ problem. The key is Lagrangian, first order condition for the Lagrangian, and then we may do simple algebra to find the optimal solution. Okay, so that's the end of this lecture video. In the class, let's do more discussions. Thank you.